Okay, we're going to look at Hooke's law, and Hooke's law relates to, well, if you take a string that is elastic, so up to now everything that we've been doing has been inelastic. That string has just been a length and that's it, it can't stretch. But now if you were to look at a string that could stretch, or if we could imagine it was a spring, okay, it's two of the same thing. Okay, so it's something that's elastic or a spring. It can stretch, and it can stretch beyond its natural length, and a force occurs as a result. So as you stretch it beyond its natural length, there is a force that's trying to effectively pull it back to its natural length. And we find that there is a proportionality to the force that's occurring to that change in its length. To cut a very long story short, there is a formula that I'll go through in a moment that is available to you on the formula tables book, and we can use it to look at an elastic string or a spring when it's being stretched and the forces that occur as a result. But let's just play around a little bit with a spring. One of the key features of a spring is that things can have a different elastic properties. So any of you who've done any work when you've been given a strap by a physiotherapist, a green one, red one, and so forth, they have different types of elasticity. And in mathematics and physics, we talk about the string's elastic constant. And again, I'll talk more about that in a moment. But I've got two strings. If I put the same weight on both of them, now you can see it's oscillating. Let's just stop it oscillating. Let's just let it just be at a natural sort of an equilibrium. Now, if I have a string that has quite a large constant, it's not going to, it's a thicker, you can see the graphic looks a bit thicker. The larger constant means it's quite strong, and therefore it's not going to stretch quite so much when you put the same force on it. Okay. Meanwhile, if you make it a really flimsy string, you're going to find that it's going to stretch further with that same constant force being, weight that's being acted upon it. Let's just reset that. Let's look at two different. Let's just stop it oscillating. We can talk about sort of how much do we need to put on something, and we might find that we can put more on. Now it's not letting me play around with the weights that I can put on there. Actually, I wonder whether I can actually take that off and put a different one on. No, it's not going to let me play around with this, so it's rather rigid, I'm afraid. I was trying to see if I could put a stronger weight on there and make it roughly. That's not too bad. So here we've got a string with a large constant, so it's quite a strong string or spring, and a large force, 250 grams, has not stretched it as far as the 100 grams on the flimsy spring that has a small spring constant, or elastic constant is what we refer to it. Okay, so now, if I just show you there's a sort of that's where its original length was, and it's extended by almost the same amount. Okay, so anyway, so the key thing here is the bigger the elastic constant, the greater the force that's required to spring it back to its natural length. We could look at, if we were to have something. We can look at gravity and look at the force and the opposite. That's when it's in equilibrium. If we set this off, you can see there that the force is changing. The blue arrow is changing. The closer it is to its natural length, the smaller the force actually is. Because as I said to you, the force is proportional to the distance that it has been displaced from its natural length. So in a sense, what we're interested in is the difference between its natural length and where it actually is. The weight is a constant. The red arrow you see there is not changing. And we've got this sort of oscillation going on as a result. If we just put it in its equilibrium. Okay, so we're going to play around with a few of these questions. Let's just get rid of one of these springs. If we just imagine, let's go back to having the same spring constant. So the idea is, okay, if I put 100 grams on, it stretches so far. If I put up 250 grams on, it stretches further, even though it's got the same elastic constant. So let's look at a few questions that involve us looking at what happens with different scenarios, different weights, different forces acting on it, different amounts of extension, okay, or stretch. So firstly, Hooke's law: when an elastic string or spring is stretched beyond its natural length, it exerts a restoring force, i.e. it's creating a force to try and restore it back to its natural length. It exerts a restoring force which is proportional to the length it is extended beyond its natural length. So F equals K brackets L minus L naught. So the L minus L naught is effectively describing the difference between its actual length at any moment in time and its natural length. Okay, and the K is the constant. So it's just a multiplication of the elastic constant by the difference, the stretch that it has had. So we're going to go through a question, but before I actually do the question, I'm going to do a very simple sort of scenario. So let's talk to the question, and I'm just going to, before I start part one, I'm just going to just go to an absolute basic level of using the formula. Okay, scale pan of mass 0.1 kilos is attached to the one end of a vertical elastic string. So we can imagine we've got our weight, our mass, it has a weight, and there is a spring or string. Generally speaking, by the way, the string is shown looking more like a spring, okay? A bit of a squiggly, spirally sort of, rather than a straight line. So it just shows that it's inelastic. Sorry, it's elastic, not inelastic. Inelastic string would be a straight line. An elastic string or a spring would be shown looking a bit like a spring. Okay, so the constant is 4.9. By the way, that it's measured in newtons per meter. And the natural length is 0.5, so 50 centimeters. With the other end of the string being attached to a point on the ceiling. Right, okay, so before I actually do this question, let's just imagine that I was going to sort of stretch it. So let's not worry about the mass at the moment of 0.1. If I was to say, for sake of argument, if I was going to stretch it to a length of 60 centimeters, so an extra 10 centimeters, what's going on? So I've got my mass multiplied by my gravity. Let's not worry about what the mass is. Let's just imagine the force that's pulling it back in the other direction. That's what we're imagining. So at 0.6, my constant is 4.9. My length is 0.6. My natural length is 0.5. So I end up with, when I do that calculation, end up with 0.49 newtons. So that's the force that's being created by the spring back in the other direction. And we obviously would have a force acting down. So now if the object had a mass such that when you multiply by 9.8, you get 0.49, okay, i.e. If it was just 50 grams, then it would be in equilibrium. If it's a larger mass, then it's going to be pulling it down and it's going to be moving. If there's no equilibrium, if the force acting up, okay, is not the same as the weight acting down, it's going to be stretching, it's going to be moving downwards. Okay, you might have this equilibrium whereby the weight created by the mass is equal to the elastic sort of force that's trying to pull it back, the restoring force pulling it back to its natural length. So let's look at the question. So here, calculate the extension if it hangs in equilibrium. So we know that K is 4.9. We know its natural length is 0.5. We're wanting to work out what its new length is. Now, just the extension, okay, is going to be the difference between those two values. Okay. And we know the mass in this instance is 0.1. So if there's equilibrium, mg going down is equal to the restoring force in the other direction. So we can say that mg is going to be equal to k multiplied by L minus L naught. So the mass is 0.1, gravity is 9.8, the K value is 4.9, and we're wanting just that extension. And rearranging that relationship, we get the extension being 0.2. So its new length in total is going to be 0.7. Okay, but the extension is 0.2. So calculate the extension in the string when the scale pan hangs in equilibrium. So the key idea is that the restoring force is equal to the force occurring as a result of gravity in the direction of the string or spring is orientated. What mass must be put on the scale pan for the string to be of length 0.9? Okay, so if we want the length to be 0.9, this is part 2. So we know that K is equal to 4.9. We want the length to be 0.9. Its original length was 0.5. The mass of this object is 0.1. So we want to know instead what other mass, what different mass. Okay, I suppose actually what we should actually appreciate is what extra mass are we going to add on to the 0.1, because we've got the empty scale pan which has a weight or mass of 100 grams, but how much extra are we going to put on to give a total that will extend it by 0.4? Okay, so if we have our new mass, let's call it M2 multiplied by G, and it's going to equal to K. Actually, I'll tell you what we'll do. We'll just write out the formula first. Sorry. K multiplied by L minus L naught. So what's my new mass multiplied by 9.8, which is going to equal to 4.9 multiplied by the difference between its new length and its original length. So tidying that up, we get 9.8 lots of the new mass being equal to, let's get my calculator out, 4.9 times by 0.4, which gives you 1.96. So my new mass needed is going to be, it's going to work out quite nicely, it's going to equal to 0.2. So therefore the extra mass that we're going to actually need is going to be that extra mass minus the pan mass. So the extra we're going to be putting on is going to be 0.1 kilos. Okay, moving on. Okay, this is a new scenario that we're going to now look in a horizontal direction. So it's not so much a mass with a weight that we're concerned about. So a particle rests on a smooth horizontal table between two vertical walls which are 4 meters apart. It is attached the left hand wall by means of elastic string with natural length of 1.2 and an elastic constant of 5, and it is attached to the right hand wall by means of an elastic string of natural length 1 meter and elastic constant of 4. So straight away we appreciate that the total distance is 4, and we've got these two strings. One's 1.2 meters and the other's 1 meter. So straight away we need to appreciate that they're going to have to extend in order to span across the 4. Let's draw a diagram. Okay, so there's your two vertical walls and a horizontal surface, which is smooth, so the object can just move freely. There's no friction occurring. Now, smart Alex amongst you will immediately make points probably about the distances. Let's assume that the particle has no width whatsoever. I know I've drawn a big fat rectangle there, but let's just imagine that it's effectively infinitesimally small. So we're not concerning ourselves with that. Let me be picking holes on that one. I know straight away as I work through this, someone's going to be saying that to themselves. Anyway, so particle rest and smooth, 4 meters apart. So we know that the entire distance between these two, let's use a different color. So the entire distance between these two walls is 4 meters. The left-hand wall, elastic string with natural length of 1.2, so L naught is 1.2 and its constant is 5, and it's been stretched a certain distance. Okay, and what we're gonna say actually is that new distance, we can call it a letter, I suppose. Let's just call that new distance, let's call it X. I could call it L1, arguably, okay, but you'll see why it's useful to call it X. Now, we've got then the right hand wall. It has a natural length of 1 meter and it has an elastic constant of 4. So it's not quite as strong, so it's more easy to extend it. And so that distance there, so that L2, what we're going to refer to L1, L2 in relation to each other. We know the whole total distance is 4, so what we can do is we can just say 4 minus X as being the distance of L2. There's forces acting upon the object as a result of the string. There's a force acting to the right, and there's a force acting to the left. F1 and F2. So find the distance of the position of equilibrium. So equilibrium is going to occur when those two forces are equal to each other. Okay, so let's go back to a decent color. So equilibrium occurs when F1 is equal to F2. So we can appreciate for F1, we've got using our formula for F being equal to K multiplied by L minus L naught, we are going to have a constant of 5, a length of X, and a natural length of 1.2, and that must equal, using the same formula, we've got K is equal to 4. We've got our our actual length being 4 minus X and our natural length being 1. So we have a formula involving just X. Solving that equation, we end up with 9X being equal to 22 minus 4, which is 18. And so X, very helpfully, is 2 meters. So it's literally halfway. So if you think of X being 2, 4 minus X is going to be 4 minus 2, which is 2. So actually, in this particular scenario, with these two springs or elastic strings, this object is actually directly in the middle. Moving on to the second part, find the two distances from the left-hand wall at which there is a resultant force of magnitude 4.5 newtons on the particle. Okay, so just to quickly explain what they're talking about here. Imagine, so at the moment we've worked out that equilibrium occurs when the object is directly in the middle. Okay, imagine if I were to then pull the object to one side or the other. So I was to pull it over to one side. We then have a situation where the spring, so pull it to the left, the spring on the right will be extended more, the spring on the left will be extended less. So there's going to be a larger force wanting to pull it back towards its equilibrium. Okay, so I could pull it off to the left. There's going to be a force, a total force, a resultant force wanting to pull it off back to the middle. Likewise, if I pulled the object over to the right hand side, I would find that there will be a force, a resultant force trying to pull it back to the center, pull it to the left back to the center. So there's a point over here where the force acting, trying to pull it towards the middle, it will be 4.5. There'll be also a point over here somewhere where it's trying to pull it back to the center, okay, where the force is 4.5. So what this question is asking is, find how far to the left and how far to the right would it need to be such that the force is 4.5 newtons. So in this equilibrium, the forces are equal to each other, but if I were to pull it one side or other, I've got to find that the difference in the forces occurring is going to be 4.5. So we could say that F1 minus F2 is going to equal to 4.5. That would be in one scenario where the force of the first spring is greater than the force of the second spring. That will occur when it's being pulled off to the right hand side. The force pulling it back toward the left is greater than the force pulling it to the right. And alternatively, I can have a situation where it's the other way around. Okay, the force pulling it to the right is greater than the force pulling it to the left, and that will occur when the object is pulled to the left hand side, and F2 is going to be greater than F1. It's going to be trying to pull it back to its point of equilibrium. Now, you can see there they're both basically the same. We could tie that up by simply saying that the difference between the two forces is plus or minus 4.5. Okay, that would be the quickest way to set this up. You could do it separately, but let's work on the whole thing as a whole. Right, so we've got expressions for F1 and F2. We've got an expression for F1, which is 5x minus 6. We've got an expression for F2, which is, it'd be 12 minus 4x. So if we subtract one from the other, we're saying that the difference between them is going to be 4.5. So now we're taking each of these separately. Okay, so if we tie this up, take the plus version. Okay, so we would end up with 9x minus 18 is equal to 4.5. Or separately, the other way around, with a minus, we'd end up with 9x minus 18 is equal to minus 4.5. And solving those two equations, and notice the algebraic wizards amongst you could have taken a different approach. You could have done a quadratic equation. You could have squared both sides. 9x minus 18 all squared is equal to 4.5 all squared, and got a quadratic equation and solved that. You still get 2.5 and 1.5 meters. Don't forget your units. So the idea here is the x, which is the distance from the left hand side. Okay, so it's stretched 2.5 meters. So if this distance here was 2.5 meters, i.e. the remainder will be 1.5, totaling 4. Or we could have it in the other direction where it's only stretched from the left hand side 1.5 and the real stretch is on the other side as such. So there are your two answers to the question. Okay, and a completely different scenario. An elastic string of natural length 0.5 meters and elastic constant of 3 newtons per meter has one end attached to a smooth horizontal table, so it's a fixed point. The other end is attached to a particle of mass 1 kilo at rest on a smooth horizontal table. So you can imagine you've got your smooth table, you've got your string connected to a fixed point, and you've got an object. Now, the particle is given a velocity so that it makes a circle or a radius 1 meter on a smooth table. So just imagine that the particle is spinning around. Okay, it's spinning around the table. We're looking at sides along the side here, but the idea it's spinning around. Now, for it to do that horizontal circular motion, we're going to have a centripetal force, and that force is going to be provided by the spring. Okay. In the same way, when you go back and look at your notes on the horizontal circular motion, you'll find that the string, the tension of the string, was giving you a force that caused it for that sort of circular acceleration, just turning. So we've got the same scenario here. So anyway, as I read it, it's given a velocity. It makes a circle of radius 1 meter on the smooth table. So when in its resting position, it's 0.5. But once it does that sort of for want of a description, circular motion, all of a sudden we have a situation where this object is further out. So it ends up being further out here. The string extends itself, and the object is further out. Okay, so there's been an extension. Get different color. There's been an extension in there's your L naught. Here now is going to be your L. Okay, from your starting point. Okay, and your mass is being pulled out. The string is creating, or the spring, sorry, is creating a force acting in, which is providing the centripetal force. So we have a weight 1g. We have a normal reaction in the other direction. Now there's no friction. There's no issues there. That's really of no consequence whatsoever. What we're really interested in is the force acting in. The force is being created by the spring. We know that K is equal to 3. Its natural length was 0.5. Its new length is 1 meter. We know that the Hooke's law states that the difference in the lengths multiplied by the constant is equal to the force created, and that force is going to give us the centripetal force. We know that centripetal force is mv squared over r, but it's also equal to omega squared r, where omega is, oh, hang on a second, what have I just done? Oh my lord, have I just lost my mate? I managed to get that back, sorry. So where omega is the angular velocity. Right, okay, and that's what we're being asked to find out here. So we're actually going to use this formula. So we can say that the force being caused by the spring is going to be 3 multiplied by 1 minus 0.5. That's my restoring force of the spring. That is going to equal to, now the mass is 1. The angular velocity we don't know, squared, and the radius Well, the radius of the circular motion is the L length, the length of the extended spring, which in this instance is given as 1. So all works out quite nicely. We've got 1.5 being equal to omega squared. So I can work out omega by doing the square root of 1.5. And that comes up as 1.22 radians per second. Fairly straightforward, hopefully. We have the last question. So we have an elastic string or spring of natural length 1.5 meters, an elastic constant of 3g, has one end attached to a smooth plane inclined at 30 degrees to the horizontal. The other end of the string is attached to a particle of mass 5 kilos, which is at rest on a smooth inclined plane. So we have our angle of 30 degrees. We have our string that has a constant of 3g. It has a natural length of 1.5. That's L naught. We want to know what its length is going to be to create the equilibrium. That's the first thing we need to find out. Okay, bear with us. So what else is going on? So we have the string is creating a force, the restoring force, up parallel to the inclined plane. It's trying to pull it up. We have gravity pulling down vertically, and we have a normal reaction to the surface. If we take the components of that gravity, we have the mass time. Now the mass is 5, so straight away I can put in 5 instead of g, so it's 5g, and the weight perpendicular to the surface is going to be 5g cos theta, and parallel to the surface is going to be 5g sine 30. If it's going to be in equilibrium, we have to find that this force here is going to have to add up to this other force in the opposite direction. So we're looking, if it's equilibrium, we're looking at the forces in the direction of travel, which is along the inclined plane. So we are saying that F is equal, restoring force from the spring is going to equal to 5g sine 30. Okay, so we need to work out what that force is. So using k brackets L minus L naught, we're going to end up with 3g multiplied by L minus 1.5. And that's going to equal to 5g multiplied by the sine of 30. Now sine of 30 is a half. And we find that, well, g can be cancelled both sides. We end up with L minus 1.5 being equal to, well, that's 5 over 2, it's 2.5, divided by 3, it's going to give you 5/6. So L is going to equal 5/6 plus 3/2, which works out as 14 over 6, 7 over 3, whatever that is in meters. 7 over 3 is going to be 2 1/3 in meters. Okay, units. So find the length of the string when the particle is in equilibrium. So 2 1/3, it was originally 1.5 and it's been extended to 2 1/3 as a result of the weight that is being held on this smooth surface that's being effectively dragged down by gravity because of the incline. The particle is pulled down the plane by 2/3 of a meter below the equilibrium position. So an extra 2/3 gives it a total new length, extended length of 3. Find its initial acceleration up the inclined plane when it is released. So what we're saying here is there's going to be an acceleration going to be going up in that direction because we've pulled the object further down the inclined plane. So setting ourselves up, so the new inclined plane, so this is part, this is a new part, so our new length is going to be 2/3 added on to 7/3. So our new length is going to be 3. Our natural length is still 1.5. Our K value is still 3G. And we want to know what the forces are occurring here. So we're looking at, there's a force acting in one direction. There is a force acting in the other direction, but they're not equal now. Because we've extended this object's distance, the force, the restoring force is going to be greater. And if we do the difference between the force and the horizontal, also the parallel component of the weight, that's going to equal F equals ma. So we can have a situation where our acceleration multiplied by the mass is going to equal to the difference between the restoring force pulling in one direction and the weight component trying to pull it in the other direction. So filling in the various values, we can work out what our force is. It's going to be K multiplied by L minus L naught. The mass is 5. The sine of the angle is still 30 degrees, so it's still sine of 30 degrees, just a half, and that's going to equal to the mass multiplied by acceleration. Acceleration is what we're trying to find out. So there's no unknowns there. We can straight away work that out, get a calculator out. And we end up with the acceleration being 2/5 of gravity. That's 3 point something. I can't remember exactly. Let me work it out. 3.92 meters per second squared is the acceleration. So F equals ma is being used here. So the sum total force acting in the direction of acceleration is equal to the mass multiplied by the acceleration. So I worked that out. Difference between the springs sort of resolving, its force wanting to pull itself back to its natural length, minus the weight component gives me that force. Okay, there's some very simple questions there, nothing too taxing, I would argue, and you should now be able to have a go at exercise 7E on page 138, and that is the last of our chapter 7.